Okay, so page 384, number 7C. So let's see what they ask here. So here they say write as a sum or difference of logarithms, simplify if possible. And 7C is log. So we know that that's log base 10 of u times v cubed. U times v cubed. All right. So here we're going to try to use the appropriate logarithm rule. And I do see an exponent here, but again, using my usual rules of BEDMAS here, the exponent applies only to the v, not to the u. Otherwise, there would be brackets here, and that's just following order of operations. This exponent gets applied before this multiplication. Okay, so that means I can't use the ski slope rule, but what I can use is the product rule first, because I've got the log of a product. And so the log of the product is the logarithm of the individual expressions. So it's going to be log of u plus log of v cubed. Okay. So again, see what I'm doing when I use the rule. I try to say what the rule is doing instead of just memorizing some big, long math sentence. Okay. Now, log of u here, not really much else I can do. But now here, we know that we can use the ski slope rule at this point because I have the logarithm of a power. And so here, this just becomes 3 log v. Okay. And what's nice about this, as we'll see, later on, we're going to see that it's nice to work with individual logarithms if we can, instead of this more complicated one. All right. So are there any questions on this here? So I forgot who had asked the question. So if you have any questions on this. So again, we had to use the product rule first because the exponent does not apply to u and v, only v. And then from there, we were able to use the ski slope rule. Okay, so if there's no questions, let's move on to the next one. And that is page 377, 11E. Page 377, number 11E. All right. Okay, so 11E is to solve for the solution to these equations. And here they actually want us to do an approximation. Okay, so normally I'd probably, just to let you know, I would probably ask for exact solutions, but here they want us to round the answers, so it'll help us practice doing that. Okay, so here we've got 3 to the x plus 1. And then here we've got plus 56 times 3 to the negative x equals 0. Okay. And what we're going to see, similar to, polynomials or rational functions, there's certain ones that are, easier to solve than others. Okay, hold on, somebody else just coming in. And we're going to see patterns here. So hopefully when you look at this and you go back to the lesson, you should see something familiar. You should see this 3 to the negative x and figure that, this negative is going to take the 3 to the vx, put it in the denominator, and it should look like a rational equation. Okay, so we're going to see that, in each of the cases that I gave you in number 11, they should look something like the ones we'd already seen. Okay, so the first thing I want to do, just to keep in mind what the strategy should be, is if you can try to get the same exponential expression showing up in each of your powers. So here, all I'm going to do is this 3 to the negative x is 1 over 3 to the x. Okay. And so now I recognize this as a rational equation. And what eventually you'll hopefully start to do is not have to do this change of variable like I'm going to do here. Okay. But for now, since this is a pretty new concept, let's actually do the change of variable. Okay, so here, if I replace 3 to the x by z, I have z plus 1 plus 56 over z is equal to 0. Okay, just give me a second. Somebody's trying to join and not able to do it. Give me just a second. Let's hope they get that message. All right, sorry about that. So now I'm just going to follow my usual rules. So I know I want to get rid of my denominators altogether, and the way to do that is to multiply both sides by the lowest common denominator. Since there's only one denominator, that just becomes my z. Okay, and then here, what do we have? Distribute, so z squared plus z times 1 is z. And then here, when I multiply the third one, the z's in the numerator and denominator reduce to 1. So I'm just left with 56. Of course, 0 times z is 0. And hey, look at this. We've seen this many times before. We've turned some different type of equation into a polynomial equation. Okay. So here, this looks like it's going to be nice and easily factorable. Okay. So what do we have? We have z and to 0. So here it's going to be z plus 8 times z plus 7. Okay, and so z is equal to -8, or z is equal to -7. Okay, and so now we know that we're not looking for z, we're looking for x. And so this is where I'm going to put z, 3 to the x equals -8, or 3 to the x is equal to -7. And this is where we see, oh, wait a minute. This is an exponential expression equal to -8. That's impossible. Okay, or even if I try taking the logarithm of both sides, let's say I take log base 3 of both sides, I have log base 3 of 3 to the x, which normally I wouldn't write. These are inverses of each other, but I'm writing it out just to show how this works. So I'm just left with x equals log base 3 of -7, and you cannot take the logarithm of a negative number. Okay. So that's perhaps why they didn't give any answer. I guess they should have said there's no solution instead of just leaving it blank. Okay. But you have to go through all this process to find out that indeed there's no value of x that is going to solve this equation. Okay. All right. Any question on this one here? Let me just kind of show the full solution. So again, to recap, use exponential properties, whatever you need to try to rewrite so that the same power shows up. From there, identify it as, whatever type of equation it is. In this case here, a rational equation. The rational equation gets turned into a polynomial equation, solve, but then you have to go back and solve the powers. Okay, I see a question there. Yeah, Krish, go ahead.
I think for this one, it doesn't factor. I think you have to use the quadratic formula.
Let's use the quadratic formula, -b plus or minus square root of b minus 4b squared, times 4 times a, which is equal to 1 times 56. And it looks like in this case here, please tell me if I'm making a mistake. It looks like I'm still going to have some negative in the square root. So whatever this is 200. What is this? 224. 1 minus 224 is -223 over 2, which looks like is going to give me the same problem of no solution. Okay, please, folks, take a look. Did I do that calculation correct? So in the end, the same result, but with the incorrect solution here. Okay, so yes, I definitely lose a mark on this one for not doing that right. Okay, sorry about that. Who asked the question? Is everything okay with it now? All right, I guess we'll leave the mistake in just so everybody can see that everybody makes this mistakes. It's not the end of the world. Okay, so if there's no questions, then let's move on to 368 5D. All right, 5D. Okay, so another solving equation, page 368, number 5D. So here we have 36 to the 3m minus 1 equals 6 to the 2m plus 5. Now, in the next lesson, we're going to see that, very clearly, not all equations are going to be able to solve in this way, where you can get the exact same power in all of your expressions. This is a very special type of example. We're going to end up with equations where you have different powers, okay? And there is going to be a strategy for solving those, but this is a very special situation, okay? Because even though I have different powers on either side of this equation, I can write them still in terms of the same power, okay? So here, what I would do is I would just start by, I could take, I guess, log base 6 of both sides and use the ski slope rule. But like I said, I don't even need to use logarithms at all here, because I notice that this is 6 squared. Okay, and then this can be reduced using the third law of exponents. So this is going to be 2 times 3, 6m minus 2. And this is 6 to the 2m plus 5. And here you could think of this as taking log base 6 of both sides, which is just going to eliminate the effect of the exponential function. Or more intuitively, I've got two powers with the same base, so that are equal. Hence, the exponents must also be equal. Okay, so this is one of those times where you can think of it intuitively, or actually show that you're taking log base 6 of both sides. Okay, and now this is easy to solve. 6 minus 2, 4m, and this is 5 plus 2 is 7. And so this looks like m is equal to 7 over 4. Okay, now if you solve this differently, say right off the bat, you took, we can show how this is going to be very similar, because if I take log base 6 of both sides, well, use the ski slope rule here, 3m minus 1. I'm left with log base 6 of 36. And then here, this, they cancel each other out because it's log base 6 of 6 to something. So 2m plus 5. And lo and behold, hey, what's log base 6 of 36 equal to? That's just equal to 2. So you see that in the end, we end up with the same equation that we would be solving. Okay, I would say this is maybe the more straightforward way, but again, we see that doing it through logarithms, we get to the exact same spot. Okay, so you can take your choice on that one there. Any questions on that for whoever asked that one? Okay, good. All right, let's move on to 368 number 13. Somebody had asked for that one. Page 368, number 13. Let's find that there. Okay, so this is the one I think we had done in class, but maybe not everybody would have been there to see that. So I'll take a look at this here. So it says, apply algebraic reasoning to show that A equals B to the log A over log B, log A over log B is true. And here, a couple of people asked me, why do they say, A has to be bigger than 0 and B has to be bigger than 0? Like, why are they talking about that? Well, I notice here that A is inside a logarithm. So I know I can't take the logarithm of a negative number or even 0. So that's why we have to specify that A is strictly greater than 0. And similarly here, I've got a log B. So that means the b value has to be strictly greater than 0 because these things are only defined for positive inputs, okay? So they're just kind of covering their bases by saying, yes, this is true all the time, only when all the terms are defined. In principle, this should be understood, but this is why they're putting them down. Okay, and we saw, I think we talked about, in one class, we talked about 2 ways of doing it, and then somebody in class had another way of doing it. There's lots of ways of working with this here. I think the way I did in class was I noticed that this expression, log A over log B, looks a lot like one of our logarithm rules. It looks a lot like the change of base formula. So if we remember what the change of base formula is, it says the logarithm of any base can be turned into the logarithm of any other base. And the rule that we proved, okay, we didn't just come up and just take it for granted. We actually proved that this was equal to log base B of the original input over log base B of the original base, okay? And if you want, you can apply this rule to log base 10. So if I was just changing this into log base 10, it would be log base 10 of the original input over log base 10 of the original base. So this is our change of base formula. So now let's use it to go backwards, okay? The logarithm in the numerator, okay, represents the input. So it's going to be a logarithm with an input of x, and the logarithm in the denominator represents the original base, okay? So, oh, sorry, not x here. Sorry about that. Logarithm of the original input here is a, and the original base is b. Sorry about that. I was looking at these values instead of these here. Let me rewrite this a little nicer. Okay, so this represents the original input, and this represents the original base. Okay, so now I can take the right-hand side, which is b to the log a over log b, and replace this exponent with what it's equal to. Okay, which is b to the log base b of a. All right. But now that I've done this replacement here, I notice that these two functions are inverses of each other. Okay, I'm taking this input and I'm putting it into the logarithm. Then I'm taking that and putting it into its inverse function, the exponential function with base b. Since these are inverses of each other, it just spits out the original input. And there's my left-hand side. Okay. So another way of solving it would be to rewrite this in exponential form. Okay. Is remember our other rule that we have that y equals log base a of x is the same as a, the base, to the exponent of y is equal to the result of x. Okay, so if I take this exponential expression and go backwards now and write it in logarithmic form, okay, what does that look like? Well, here, remember that this represents the base of the logarithm. Okay, so the base is b. Okay, this represents excuse me, where are we here? Let's go. So this represents the base. Okay, the thing inside the logarithm represents the result. So the result here is the thing inside the logarithm. Okay, and the exponent here is what the logarithm is equal to. Sorry, log base, log of a over log of b. And look what we have. We know these two things are equal by the change of base formula. Okay. So either way, whether you use the change of base formula before or after, somebody else said they solved it by just taking log base b of both sides. That works too. Any one of these proofs would be sufficient. So here we use the change of base formula right away. Here we changed an exponential expression into a logarithmic one, and we showed this is true because of the change of base formula, and there's probably several other methods to do that. Okay. Now, the person who asked the question, do you want me to do it in that third way, or are you okay with what I've shown? So if you can just give me, if either of these didn't make sense to you, I can show you yet another way. Okay. So we'll call this method number 1. We'll call this method number 2. Okay. Method number 3, and this is maybe the one you have to think a little bit about. Okay. Is let's take log base b of both sides. Okay. So here I have log base b of a, and then log base b of b to the log a over log b. Okay, so here there's nothing to simplify, just log base b of a. But here we have inverses. We have this input is being put into the exponential function, which is then being input into its logarithmic inverse. So these two functions essentially cancel out each other's effects. So I'm just left with the original input, which is log a over log b. And yet again, these two things are equal because of the change of base formula. Okay. So 3 different ways of seeing it. But in the end, you have to make some sort of reference to the change of base formula. Okay. Okay, any other questions on this here? Okay, so somebody just put in page 377, number 10. Number 10, okay. (377) number 10. So here it says, does this equation have any real solution? Explain your answer. All right, so here, got another equation here, 4 to the 2x plus 2 times 4 to the x, and then plus 3 equals 0. Okay, so again, I look at this here and I see that I've got the same base, but I don't quite have the exact same power, because here it's 4 to the x, here it's 4 to the 2x. So you want to ask yourself, is there a way to rewrite one of these, presumably that one here, which is the more complex one, so it has the exact same power showing up? And here, hopefully you say, hey, the third law of logarithms, where you multiply the exponents, I can rewrite this as 4 to the x squared. Okay, because 2 times x, 2x, there you go, they're equal to each other. And so at this point here, you then again hopefully recognize this as looking a lot like a quadratic. And like we did before, if you kind of want to really show that more explicitly, you can replace 4 to the x by some other variable, and then all of a sudden you realize this is essentially a quadratic type equation. Okay, so here I will attempt to factor this correctly. I feel I'm going to be a little more careful now. Sorry, here we've got z minus 1 and z plus 3. Okay, so what do we have? We've got our, oh no, sorry, that doesn't work. So it looks like this is not, no, this is not factorable. Wow, my factoring today is way off. Okay, since they're both positive, let me just check. Yes, they're both positive. This is not going to factor. Okay, so here, let me use the quadratic formula. So negative b plus or minus square root of b squared. So that's 4 minus 4 times a times c. Okay, all over 2a, 2 times 1. And here, negative 2 plus or minus 4 minus, there we go, 4 minus 12 is negative 8 over 2. Hence, there's no solution. Okay, so there's no point in even replacing z by 4 to the x, because 4 to the x would end up being equal to something that doesn't exist. Okay, and so there you go. There's nowhere else to go any further. Okay, so keep in mind, in this case and the one we saw earlier, okay, the quadratic itself had no solution. Okay, but then we saw another one where the quadratic might have solutions, but sometimes one of them ends up not being valid. So as we saw in class, that if you end up with 4 to the x equals negative 7, okay, similar to one of the ones we saw earlier, that might be another reason why you don't have a solution. It could be the polynomial has no solution, like this case here, or it could be the resulting exponential equation that has no solution. You have to be on the lookout for both. Okay, so let's say I want to prove that the logarithm of a quotient is equal to the difference of the individual logarithms. Okay, now when we did this, we didn't have the end result. Okay, but the idea is we said, well, if I were, say, given to prove this, I would say, oh, look, I've got a division, I've got a subtraction. That looks a lot like the second law of exponents, where you have a to the x divided by a to the y is equal to a to the x minus y. Okay, and this was our starting point. We said, I want to find something to do with logarithms that's going to be related to this second law of exponents. Okay, so since we're working with two exponential expressions in the exponential law, we decided it made sense to start with two logarithmic expressions in our proof. So we said, let's take a logarithmic expression. Why did I give it the name m? Because the goal was to eventually write it in exponential form, so I could hopefully use this property here. Okay, and then I defined a second one. Okay, again, two logarithmic expressions. I gave each of them a name, so that now the next step would be to rewrite these in exponential form. So this is equivalent to a to the m equals x, and this is equivalent to base a to the exponent n is equal to y. All right, and the reason why this is useful is because now I can make use of my exponential property, my exponent law. Okay, so I'm going to divide the two left-hand sides. Okay, but then that's going to be equal to the division of the two right-hand sides, since left side and right side are equal. Okay, and now the reason for doing this is so I can apply this rule. In the first law of logarithms, we multiplied them, so we could use the first law of exponents. For the third one, we took one of these powers to another power so that we could use the third law of exponents. So here we apply it and we got a m minus n is equal to x over y. Okay, so now that we've applied the exponent law, that's as far as we can go. Now we want to turn things back into logarithmic expressions. And so here, I don't want to have this exponential expression anymore. So how do I get rid of an exponential expression? I use its inverse. So we took log base A of both sides. And so this accomplishes what we wanted to do. These are inverses, so they eliminate each other's effects. So I'm just left with the original input, m minus n. And of course, we remember that m and n are just these logarithms that I originally defined. So m is log base a of x, n is log base a of y. So I'm just going to replace that in the equation. And here we go. We have our second law of logarithms. Okay. And the nice thing about proving it is not only did we prove it, we didn't pick any specific base. So that means this works for any base as long as they're the same. We didn't choose any specific inputs x and y. We didn't just do it for log, base 3 of 7 and log base 3 of 8. Any base and any input, of course, assuming that they're valid. So for the inputs, they have to be greater than 0. For the bases, it has to be greater than 0, not equal to 1. This works all the time. Okay. But what I really want you to get out of this proof is two things. First of all, that this doesn't come from nowhere. Okay. We've proved it. We now know it is true. It's not just something I threw at you and told you to use. We know it's true. But what I also want you to see is this idea of how useful it is to toggle between exponential and logarithmic forms when you're trying to prove things. Okay. So when we do some more complex examples later on, okay, we're going to see that this is a useful tool.